Okay, good morning, students. Let's continue our lecture for this weekend. A lot of you are not here, but let's start because the recordings will be there. So we continue with our algebraic expressions. Today we want to look at our subtopic called changing the subject of a formula. Changing the subject of a formula. Or when you were at the lower levels, it used to be called change in subject. Change in subject. So change in subject because sometimes you are interested in a certain alphabet. So the alphabet you are interested in will always be on the left-hand side of the equation when you are done with the change of subject. So on the left-hand side, you will have the alphabet of interest. Alphabet of interest. That's the result you want. And then all other alphabets or numbers will be on the right-hand side. So that is the technique we are going to use. All other alphabets and then possibly all others like numbers will also be on the right-hand side. And then the subject of interest will always be on the left-hand side of the equation. There are three types or three forms. The first one is when the alphabet of interest or subject of interest is appearing only once in the algebraic expressions. Then the second type is when the alphabet or the subject of interest is appearing twice in the algebraic expression. And then finally, you can have another type where the alphabet of interest is raised to a certain power. Those ones looks more difficult. So let's learn how to do all three if you come across them. So let's start with the simplest, the first one, when the alphabet appears once. Look at this algebraic expressions. You have S on the left-hand side equals D divided by T on the right-hand side. So if I ask you a question that make T the subject, make the letter T the subject. The meaning is that I want T to stand alone on the left-hand side of the equation. So if you have the equal sign, I want T to stand alone here. And then all the others can come on the right-hand side. So the steps of solving this one is you have S equals D divided by T. I want T on the right. What do? I have to do something for T to move from the right to the left. So you remember your change of subject, and then you remember your cross multiplication. Any letter or any number standing alone is the same as divided by 1. Any letter divided by 1 is the same letter. Any number divided by 1 is the same number. So when you have it this way, then you cross multiply. You try to remember your cross multiplication. So you try and cross multiply. You go this way, T will multiply S, and then D will multiply 1. So you have S times T this way is equal to 1 multiplied multiplied by D. That's the cross multiplication. So you go diagonal, S times T, and then 1 times D. S times T will give you ST. It's equal to 1 times D will give you the same D. It is T we are looking for. We want T to stand alone. So you divide every side by the number or letter attached to it. In this case, it's S. So you divide this side by S. You divide that side by S. And then you can do some cancellation. S will cancel itself. And then the T that you want to stand alone can now stand alone as T is equal to D divided by S. And this is the answer we are looking for. That when T stands alone, S will have to go and divide D. And that is the final answer you are seeing here. That for T to stand alone, it means that S will have to go and divide D. And that's our first example, which conforms to this one when the subject is appearing once. So you saw that T is appearing once. T was appearing once, and we've been able to make T stand alone. Let's look at our second example, still the subject appearing once. This time we have Y is equal to mx plus c. Y is equal to mx plus c. This one too, the subject is appearing once. What do you want to do? They say make X the subject. Make the letter X the subject. In other words, let X stand alone on the left-hand side of the equation. So let's see how we do this. Once X is on the right, let's see how we bring it to the left. You have Y equals mx plus c. What I normally advise is that you do a swap when it is straight like this. You do what we call a swap. So a swap means take everything on the right, mx plus c, and then write it on the left, mx plus c. And then you bring your equal sign. And then you swap. Take everything on the left, y, and bring it to the right. As you took everything on the left, everything on the right to the left this way, you're also taking everything from the left to the right. So y now appears here. That is the swap. Okay. It's like when you are standing in front of people. If you are standing in front of your people, this is your left. This is your right. Sorry. This is your right. This is your left. That is when you are standing in front of people. But when you turn your back against people again, this time you have turned your back. When you turn your back, you see that your right becomes your left, and your left becomes your right. So that is the kind of swap I'm doing. Y has swapped to the right, and then mx plus c also swaps to the left. So you have mx plus c equals y. We are being asked to make x the subject. So all other things will go so that x can stand alone here. So c will have to move. We have mx now equals y is there already. C is going to join. C has positive. So when it crosses the equal sign, it becomes a negative, like this. It is x we are looking for, so we want x to stand alone. And the only way you can make x stand alone is to divide both sides by the number or letter attached to x, which is m. So we divide every side by the m, this side by the m. And then we do some cancellation. M will cancel itself. And then the x we are looking for can now stand alone as x equals y minus c divided by m. And this becomes our change of subjects, that anytime we want x to stand alone, it means you have to subtract c from y and you divide it by m. And that is the second example. Then let's still look at a third example. We are still doing the form in which the subject appears once. This is our third example. Our third example is V equals 1/3 pi r squared h. This time, what do we want to do? We want to make h the subject. We want to make h the subject. In other words, we want h to stand alone. So we still continue with this swap thing. Because we want h on the left, swap the whole of this to the left, and then swap the whole of this to the right. That's the first thing you do. So we are swapping the whole right to the left. We have 1/3 pi r squared h is equal to the letter V. So that is the swap. Our right has now become our left, and our left has now become our right. We need h to stand alone, so all these stuffs here will have to go. So how do we do that? We divide every side by what you are seeing here, 1/3 pi r squared. We do same thing here, divided by 1/3 pi r squared. Then we do some cancellation. All this will cancel all that. And then the h can now stand alone by this. It's equal to, but we have a difficulty here. We have some over and over. The overs are 2. So we have to be able to convert 1 to the normal division, you know. So we can rewrite this one as V. Instead of this long division sign, we use the traditional division sign like this. So V divided by, then you have 1/3 pi r squared. Then the next thing to do is to tidy up the side. We write our V divided by, so this 1 multiplied by pi r squared, you have the same thing, pi r squared divided by 3. Then you remember when we're doing the board mass, anytime you have division, you can be able to change it to multiplication. That's what we want to do here. So let me continue here. You have h is equal to v. We are changing the division sign to multiplication, the law of reciprocity. So once we change it to multiplication, then the 3 will move up. And then the pi r squared will come to the denominator position. So finally, we have h equals, we multiply the v by the 3, and we have 3v divided by the pi r squared. And that is the end of our solution. That when you want h to stand alone, you multiply 3 by v and then divide by pi r squared. And that is the change of subject for h if it is appearing once. So if you look at the forms we introduced, when the subject is appearing once, we have done 3 examples so far. Let's look at the second form when the subject is appearing twice. When the subject is appearing twice, or when the letter is appearing twice. Let's see how to go about it. This will be our first example on that. Look at the expression. It says tyx is equal to t minus 7x.
Sir, please, I have a question.
Yes, go ahead.
So please, so in the case that you have the expression and you don't do the swapping by moving left to right, then right to left, can you still attain the same answer?
Yes, you can, but the swapping makes it looks more easier because the objective is to bring whatever letter you are looking for to bring it to the left. That is the agenda. So first of all, when you make it appear on the left, it becomes easier. But you can also use other ways and you arrive at the same results. No problem about that.
Okay. Yeah, thank you.
Any other question on this same issue? Any other question? If it is appearing once. Okay, so let's go on as we go along. If you have a question, please do ask and clear your mind before we move to the next stage. All right, so I was saying initially that today we want to tackle 3 forms. 3 forms. The 3 forms are as follows. First of all, you see that the subject or what you are looking for is appearing once. That is it. First of all, the subject will appear once. Those are the 3 examples we have done. And then secondly, I'm saying sometimes the subject or the letter you are looking for is going to appear twice in the expression. That is where we are now. When we finish, we'll look at the third form, whereby the subject will have to be raised to a certain power. And you need to bring the power down to be able to let the subject stand alone. So that is the 3 forms we are looking at. And we've done 3 examples for this one. When the subject is appearing once. Let's now look at the case where the subject is appearing twice. And I want to start with this example. I'm saying that this example, you've been given tyx is equal to t minus 7x. Look at something. T is appearing twice. X is also appearing twice. Now the question is, make X the subject. It means that we should concentrate on X. Make X the subject means that let X stand alone. Let X stand alone. That is the meaning of making X the subject. So let's see how we can do that. Let's see how we can make X stand alone. Let me write it this time above here so you can see what we are doing. So we have T, Y, X, like this, is equal to T minus 7X. And all we are doing is that we are making X the subject. Make X the subject. All right. Make X the subject means that let X stand alone at the left-hand side of the equation. Make X stand alone at the left-hand side of the equation. So that is the new direction we are taking now. Because X is appearing at both the left and the right, but we want to restrict it to be at the left alone like this, so that all other things will come to the right, and then X can only be at the left. So let's do that. Now this one, there's no need doing the swapping, because when you even do the swapping, you still have X here, you still have X here. So this time we concentrate on the X on the right and find a way of bringing it to the left. So we repeat the T, Y, X. Because it has X, it qualifies to be on the left. Then, before we bring the equal sign, we move negative 7X to the left. It is carrying a negative sign. So the moment it crosses the equal sign, it becomes a positive. So it becomes positive X is equal to T. And then now we see X appearing here. We see X appearing here. It means that X is common to both terms. Once it's common, you pull it out like this as X. Then you open your bracket and ask yourself, after pulling X out, what is left here? You have TY plus, after pulling X out here, what do you have? 7 is equal to T. So thankfully, we can see that X is standing alone now, but it's being attached with this expression. The only way of getting this one away is to divide every side by the same thing. So TY plus 7. And then whatever you do on the left, you do the same on the right. TY plus 7. Then you do your cancellation. All this will cancel all that. So X can stand alone. So therefore, X can be written as the right-hand side, T divided by TY plus 7 as our final answer. So this will be the final answer. This will be the final answer. X equals T over TY plus 7. And that is what you are seeing in your notes, that finally X will be equal to TY, T over TY plus 7. So take note of that. Take note of that. That's our first example. Let's look at another one. Same subject appearing twice. This time we have some algebraic fractional expression. And our second example is saying that P equals 3 over T plus 7 over R. And our responsibility now is to make T the subject. We are supposed to make T the subject. Let's see how we can get it right. So the question is P is equal to 3 over T plus 7 over R. Now somebody will ask, subject appears twice. But when you look through this, nothing is appearing twice. P is appearing once. T is appearing once. R is appearing once. So how come we are solving it under subject appears twice? Well, when we get to a point, you will know that this T will appear twice. This R will also appear twice. At the initial stages, you will not see it. But in the course of the working, you see them appearing twice. Let's try our solution and then see the application of what I'm talking about. Now, the first thing you do is, because they are fractions, you find LCM. That's the first thing you do, LCM. LCM of two letters means just multiply the two letters, T and R. So you have TR this way. T will come into TR, means that cover T, and then R will be left. So T comes into TR, R times 3, you have 3R plus R also comes into TR, you cover R, so it becomes T. T times 7, you have 7T. So it means we have P is equal to 7T. Now, I also told you that anytime a letter is standing alone, it's the same as divided by 1. So when you have a fraction on the left and a fraction on the right, you can do cross multiplication. So this will multiply this, and then this will also multiply that. When you do it that way, then this is the expression you are going to have now. So you have P times TR, which becomes P T R is equal to 1 times 3R plus 3. You have 3R plus 7T. So in this case, T has appeared twice. I see T here and I see T here. That is why this question is falling under subject appearing twice. So we need to find a way of bringing this T to join this T here on the left-hand side. We have P, T, R, and then this is positive. The moment it crosses, it becomes negative. So negative 7T is equal to 3R this way. Then we look for the common terms. I have T here, I have T here. So you pull T out. When you pull T out, what are you left here? You have PR. You bring your minus sign. When you pull T here, you have 7 left. It's equal to 3R. What can you do for T to stand alone? It means divide every side by what is attached to it. PR minus 7. And then you do the same thing here. Divide it by PR minus 7. Then you do your cancellation. So this whole thing will cancel this whole stuff. Now the T we are looking for is now standing alone. So you have T now is equal to the right-hand side, 3R divided by PR minus 7 as our final answer. When you are making T the subject, it means you have to divide 3R by PR minus 7. Any question on the second example before I proceed? Any question on the second example? All right. Okay, so let's continue. Let's move to the next one now. The last one we are looking at under this topic is when I said the subject will be raised to a power. The subject will be raised to a power. Those who have forgotten about how we started, let me take you back. And then you can have some understanding of what we are doing. Now, when we started, we said the change of subject, there are 3 types or 3 forms. The first form is when the subject or the letter of interest is appearing once. The second form is when it is appearing twice. And then the last form is when the subject is raised to a certain power. That is where we are now. When the subject is raised to a certain power. Let's see how we can deal with such situations and then how to handle them at the end of the day. This is our first example. It looks a bit scary, but we will do it. Now, our demand here is that they want us to make X the subject. They want us to make X the subject. Making X the subject, like I keep consistently explaining, is that they want X to be able to stand alone on the left-hand side of the equation. Look at where X is hiding. X, we need X at the left. This X, we need it to come to the left. Okay. But it is hiding under a root sign or a square root sign. And so it is difficult bringing it direct. We need to do something about the square root sign. Take X out of the square root sign before we can take it out from the right and bring it to the left. And that is the form that we see the subject is raised to a certain power. Okay, let's see how to solve such a problem when you encounter them. The question says y equals p plus the square root sign r divided by x this way. And our target is to get the x of the way. So this is what we do. First of all, we should do the swap again. The swap I did mention to you about. So we are picking all those on the right. We are swapping them to the left. And all those on the left, we are swapping them to the right. So in rewriting, we have this expression, P plus, then you have your square root sign, R over X is equal to Y. In that case, everything will have to get off here and then X will stand alone here. So P is starting the movement, P is moving, P is positive. So when it crosses the equal sign, it becomes negative. So we have square root like this of R over X is equal to y minus p this way. Then the next thing to clear is the square root, which is worrying us. So let me repeat it up here. Square root r divided by x is equal to y minus p. Now, anytime a square root is crossing an equal sign, that's what we are doing. Anytime a square root is crossing an equal sign, in fact, this square root sign you are seeing, its main name like this, when it's like this, is called a root sign. It's called a root sign. Okay. It becomes a square root when you see a small 2 written here. The moment you see the small 2 written here, then it has its full name as square root. Okay. But in many books, what happens is that sometimes they do not bring the small 2 you are seeing here. They do not bring it. They just write the sign this way as square root. But actually, there is some 2 hiding here in which we don't write. So this that you are seeing, there's a small 2 hiding here, which we can write, which normally is not written. Okay. Now this root sign is crossing over to the other side. The moment it crosses to the other side, this is what happens. You have r divided by x standing alone like this is equal to, now this whole stuff here is moving to the right. And when it appears here, this time it's not going to hide here. It's rather going to become a superscript. The 2 will come and rather sit on top here. That is the movement. So anytime a square root crosses an equal sign, it becomes a square. That's what I want to say. Anytime a square root crosses an equal sign, it becomes a square. Good. So at least we have now relieved this complex thing and it's becoming simple now. And I also did mention that anytime you have a fraction, r over x, any number standing alone is the same as divided by 1. It doesn't change anything. So once you have 2 fractions, a fraction on the left, a fraction on the right, then you have to think of cross multiplication. So it means that this one will multiply this r, and then this x will multiply this y minus p all squared. So then the arrangement becomes as follows, that we have r multiplied by 1 is equal to x is equal to x multiplied by y minus p all squared. R multiplied by r, you have r. X multiplied by this means they are attached. So you have x into y minus p all squared. Now let's go back to the question. The question says that make x the subject. Make x the subject, not r. Make x the subject. So let's see how we can make x the subject now. We have r equals x, y minus p all squared. If we want to make x the subject, it has to be on the left-hand side. So we do the swap. All this will move to the left. So we have x into y minus p all squared. And then the swap, then r goes to the other side like this. Now we have x here. X can stand alone, but we need to clear what is attached to x. So to clear what is attached to x, we divide every side by what is attached to x. That is y minus p all squared. Whatever you do on the left, you do the same on the right. So divided by y minus p all squared. Then at this point, you do your cancellation. The whole of this will cancel the whole of that. Then x can now stand alone. So for x to stand alone, we have x finally is equal to r divided by y minus p all squared as our final answer. So it means that x finally will be equal to r divided by y minus p all squared. And that is the answer we are seeing here. X is equal to r divided by y minus p all squared. Any question about this long solution? Any question about this long solution? For the third form, which is raised to the power 2. All right, so if there
I
is
have
no
a
question,
question. I have a question, sir.
yes, go ahead.
Okay, so sir, with regards to the roots x over roots r over x equal to y minus p. Now, in some mathematical cases, it is said that the roots can also represent half. In other words, the root is equal to half. So in that scenario, can we multiply the expression roots r over x times 1 over 2 to clear the roots?
No, if you do it that way, you can make a mistake. It is what you are saying is actually indices. So in indices, this thing you are seeing here, we could have written it as r over x, and then we change this root sign to half. So what happens is that it is this half power that is crossing to the other side. And whenever a power crosses, if it is like this, the moment it gets here, the 2 will come up and the 1 will come down. That is a rule. So that was why if 2 comes up and 1 comes down, 2 divided by 1 will become 2. And that's the 2 you are seeing here. But I was making it simple for you that anytime a square root sign crosses the equal sign, it becomes a square. That one is easier to remember. Is it okay?
Yes, sir. So in change of subject, this is how it's supposed to be. You don't multiply by the half.
Yes, you don't multiply by the half. In change of
Okay.
subject, anytime it crosses, it becomes a square. And then that's a good question you have asked me. Assuming it is not 2 that is written here, but it is rather cubic. Sometimes they will change it. Sometimes you see them write the 3 here. If it is 3 here, when it crosses, the top becomes 3 like this here. Uh, if it is 4, if they put 4 here, when it crosses, it becomes 4 here. So that is the movement, yes. So that is the movement of those signs.
Okay.
But I said traditionally, the square root sign, they don't even write the 2 here for you to know, but there's a 2 here that anytime you cross, it becomes a square. All right, good. Yes, any other
Okay.
question?
Thank you, sir.
Yes, thank you. Any other question on this solution raised to the power? Okay, so I'm sure let's continue once.
Yes,
Yes, Abraham, yeah,
good morning, sir.
morning.
All right. The previous one, when you look at it, you will see that there is an R at the top and then there is an R beside the P. So since we were looking for T in that, after setting free the T, that means that is the final answer.
Yes,
Oh,
because the question says that we should make T the subject.
okay.
Yes. Uh, Assuming they said we should make R the subject, then things would have changed.
Okay.
Uh,
Okay.
so anything they say make it the subject, at the end of the day, it should stand alone at the left. Should stand alone at the left. That is the essence of change of subjects. Anything they say, make it the subject. At the end of the day, that thing should come and stand alone.
Oh, thank you.
Okay, right. Any other question on the examples we have done so far? Okay, so let's move. If there are no questions, let's move to a new area which you have, come across throughout your first cycle education and second cycle education. Very important. In fact, it's one of the basic geometrical calculations which everybody who has gone to school must understand. If at this level you don't understand these three things, then let's work together. These are the things that are used to design all the beautiful things that you are seeing. I'm sure most of you have heard about these terms I'm about to write. I'm sure you've heard about 1D. You've heard about 2D. You've heard about 3D. In fact, now there are certain televisions that are being manufactured. When you are not careful and you are watching, you see the human beings as if they are walking to your room. That is the 3D. Now, the 2D is the normal TV we watch. Everything is horizontal and vertical. And then 1D is a line. So what does the D means? The D means dimension. The D means dimension. Okay, dimension. So dimension means you are having a measurement. So 1D means one dimension. 2D means two dimension. 3D means three dimension. And that is where the world is now. We are now operating at a three dimension. Now, why all this? Let me give you an example. When you have a straight line like this, or like this, it is just moving in one direction. This one, either we are moving up, or this one, we are moving down. So this one, we are either moving right. So let's say this is right movement. And then this one to left movement. This one to up movement. This one to down movement. So in all these directions, you are seeing only one direction. And that one direction is what we call the 1D. Now, the 1D, what mathematical term do we use to represent the 1D? It is what you have known all this while. That is called the perimeter. Anytime you hear about the perimeter of a particular jurisdiction, it's just talking about the distance around the outside of the figure you are dealing with. one direction. So if I have this figure like this, and I decide to move around it, so, and I take this direction, of course, you know that if I want to come back to my initial position, I'll just be going around the thing like this until I come back to my initial position. When you do this navigation, we say you are performing a perimeter. You are walking around the thing in one direction, and that's the 1D. Okay. It doesn't stop there. Then sometimes too, there's a system like the way we were plotting at the lower levels. You were told that we have y-axis and then we have x-axis. So now the direction is no more 1. Now the direction becomes 2. We have y-axis, we have x-axis. So whilst x-axis is moving horizontal, y-axis is moving vertical. In that case, we have 2 directions, the horizontal direction and the vertical direction. And this is what we call the 2D, the 2-dimensional. Now, 2-dimensional means you always have a length, which is the horizontal, and you always have a breadth or a width, which is the y-axis. So you see that we use 2-dimensional to create images like a rectangle. Before you can create a rectangle, you need 2 directions. You need a horizontal direction. You need a vertical direction. If you want to create a square, the same thing. You need a vertical direction. You need a horizontal direction. So when you are moving around an object with these 2 directions, which is called 2D, the mathematical name we give to it is called the area. Anytime you hear about the area of an object, it means that you are performing 2 directions at the same time around the object. So if I have a square, there's no need moving around all it. I can only do the horizontal movement and then I'll do the vertical movement. Why? If I do that, what I get here is the same thing that will be recorded at the top. Again, what I get by the side is the same thing I also get at the side, because the 2 directions are working at the same time. And that is 2D. Now, the modern technology now is not using 2D, it's not using 1D, it is using 3D. So that's our next one to look at. What is a 3D figure? What is a 3D system? Now, 3D means that if you look at the 1D, the perimeter, we were through only one direction. So our concern was measuring length. If you look at 2D, our direction were 2. We had the horizontal direction and we had the vertical direction. So in that case, you have length and then you have width. So 2 directions, length and width. First one direction, length. Now the 3D means that we are going to have 3 directions. And this is how it works. If this is a point and want to go 3D, we first of all go vertical like this, which we call the width. And then we go horizontal like this, which we call the length. And then we can now go through another direction like this, which we call the height. So 3D means that we are moving in 3 directions: the length, the width, the height. What object can we use to represent 3D? And this is what we can do. The normal Ludo die we've been using to play. If you look at the construction of the Ludo die, it's in the form of a cuboid where you have the numbers written 1 to 6. So for instance, if you have the numbers as follows, so maybe you have 1 here, you have 2 here, you have 3 here, you have 4 here, you have 5 here, you have 6 here. So if you look at the drawing, you see that you are seeing something like this. Look at the upper part. You are seeing this, you are seeing this, you are seeing that. That is the 3D. So you see a direction going this way, a direction going that way, a direction going this way. And that is the 3D, where you have the 3 measurements. So you have the width, you have the length, you have the height. So every 3D will give you length multiplied by width multiplied by height. Now, the mathematical name for this 3D that we want to look at this morning is what we call the volume of an object. The volume of an object becomes like a container. And that is what is used for your information. That is what is used to design all the boxes that are coming from the factory. All the boxes that are coming from the factory. So if you like, just take a box that contains any item. If you look at the box, the way the box has been constructed, you see that it follows a 3D design. You have the length, you have the breadth, you have the width. So you see the direction. So you see this direction, you see this direction, you see this direction. That is what is used to design almost everything that looks like a box. And so for every box, there are 3 things you can calculate on the box. You can calculate the volume of the box. You can calculate the area of the box. You can calculate the perimeter of the box. How can this be done? Let me illustrate it for you one more time here so you can understand the argument I'm putting across. Let's take the box, last example I gave. I'm going to dismantle a box. And then you can see all these 3 things that we want to learn how to calculate today. The perimeter of an object, the area of an object, and then the volume of an object. Let's see how we can calculate the 3 at the same time using the techniques I'm about to apply. So look at the box, the cuboid. So every box is of this form. You have the lower part, you have the upper part. And so the lower part, let me shade the lower part so the box can be clear. So this is the lower part, and then this is the upper part. So when I want to get the volume of this box, all I need is that let me measure the length. Let me also measure the width. And then let me measure the height. Once I do that, I can get a volume. for this box. And sometimes you see the volumes written around the boxes for you to know the measurement. Now, what if I want to know the area of this box and not the volume? I'm interested in the area. If I'm interested in the area, then I need to dismantle the box. And look at how the dismantle happens. So now I'm opening the box up. So this is the base that I shaded in the first drawing. This is the base. So I'm now opening up. So I'll flap the side this way. I'll also flap the side. I'll also flap the side. I'm flapping the side. So that's what I'm doing now. So I've started the dismantling. So I go this way. I flap the side. And then this one also, I flap the side. I flap the top that is covering it. Then I flap the left side. I flap the right side. So that when I want to put the boxes together, it becomes easier. All I do is that I'll lift this one up. 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 And then I'll lift the cover also up. So if I want to do the area for this one, all I need is I just need the length, and then I need the width, or what we call the breadth. And these two alone can help me to find the area. So in other words, I can find the area here. I can find the area here because all of them are having length and width. I can find the area here. So several areas. And then I'll put all of them together. Area 1, area 2, area 3, area 4, area 5, area 6. But when it came to the volume, you could find it only once here as one big volume for the whole thing by using the length, the width, and the height. So this was 3D, 3-dimension. This is 2D, 2-dimension. Then the 1-dimension, if I also want to find the perimeter, which is the last one, it also becomes easier. I'm going to dismantle. Now look at this one. I dismantled this one and I had the area. Now I'm also going to dismantle the area to get the perimeter. And look at how it will go. Look at area 1. So I have the sign. So I have 1, and then I go here, 2, and then I come here, 3, and then look at this side, 4, look at this side and this side, 5 and 6. Then we come here, 7, we go here, 8, we do this one, 9, you go this way, 10, you come this way, 11, you go this way, 12, you come this way, 13, then I'm here now, 14, I'm left with the last 2, so 15, 16, 15, 16, then the last 3, 17, 18, 19, 20. Now, when you do something like this, it is easier to add them. For instance, if this is 2, this is 1. So it becomes 2, 1, 2, 1, 2, 1, 2, 1 in little bits. So the addition of 2s and 1s becomes easier. Now, when you do this, we say you are going round. You are going round the object. And that's the essence of perimeter. So this one becomes 1D. Now, all that I'm trying to push across is that there's a way you can change volume to become area. And there's a way you can also change area to become a perimeter. In the same way, there's a way you can change perimeter to become an area. And there's a way you can change an area also to become a volume. What are the ways? These are the ways we have outlined. That anytime you want perimeter, it means go around the object and then add up the measurement you are seeing. You are just going around. So go around the object and add. If you want to find area, very simple. Look for the length, look for the width, and then multiply them. You get the area. If you want the volume, very simple. Look for the length, look for the width, look for the height, and that will give you the volume. Let's put this theory into practice. I always like to use a natural example so you can understand. Now, assuming you have this box, you are in a company and you have designed this box to put in some stuff and cover it, your products, and cover it. Now, how do you get the volume of this dimension? This is a 3D. From what we have done, this box is a 3D. And for every 3D, you have 3 directions. First direction, length. Second direction, width. Third direction, height. So we just need the values for this and then we get our volume. So volume equals length times width times height. Length is 12 millimeters. Multiplied by width is 2 millimeters. Width is 3 millimeters. 2 millimeters. Height is 3 millimeters. When you put all this together, you have 72. Now watch the millimeters. You have millimeter multiplied by millimeter multiplied by millimeter. So we write it as millimeter cube, meaning the millimeters are raised to the power 3. So this will be our final volume. That this object you are seeing here has a volume of 72 millimeters cube. Now let's look at life application. If you are manufacturing a cereal and then you want to bag them at the design or packaging unit, what things do you consider to be able to get a standard volume of what you are packaging? So this is a word problem of volume. Let's see how it can be done. It says a cereal box has a length of 20.3 centimeters, a width of 4.45 centimeters, and a height of 30.8 centimeters. The moment you see these dimensions given you, length, width, height, then your mind should start changing, that you are going 3D, not 2D, because you've been given 3 different measurements. how much cereal would the box hold? How much cereal would the box hold? So all the boxes we have been seeing in the products we buy, whether it is a Lipton or whether it is Milo, any product that is put in a box, these calculations are done before they are packaged. So let's see the weight for this cereal box. Let's see the volume it can hold. Now we know that volume is given as length times width times height, 3D. We expect 3 directions. So this direction, and that direction, 3D. And we are being asked to find how much. The how much means that what is the volume? How much cereal will the box be able to hold? That's the volume. Okay, so they may not tell you to directly find the volume, but you yourself should know that when they are asking you how much cereal will the box hold, it's about the volume. So you take your time, you pick your calculator, and I'm sure one of you is having a calculator because I'll ask for the answer. So let's multiply 20.32 centimeters by the width is 4.45 centimeters by the height is 30.80 centimeters. Let me see anybody with a calculator who has been able to multiply all these three and give me the final answer. Let me write 20.32 multiplied by 4.45 multiplied by 30.80. Abraham, have you done it?
Yes, please. So I have 2,782.318 centimeters.
0.8.
0.318.
0.318.
Yes.
So 0.318. What should I write? What should I write? Yes, I know 2782.318. You say what should I write here? Centimeters.
Yes, please.
Now, is it centimeters? We have centimeters times centimeters times centimeters. So what will it become?
Centimeters cube.
Very good. That was what I was expecting. Centimeters cube. Very good. Okay. So this is the volume. So sometimes when you see these things written on a box, it's not for fun. It means they have used the formula to do the calculation for you to know the kind of volume that you have in the system. Any question before I move to the next example? Any question about the 1 dimension, the 2 dimension, the 3 dimension? We have just solved an example of a 3 dimension. Yes, Anthony.
Sorry, I was just
Okay. All right.
itching my head.
No problem. Okay, so let's look at the second example. I told you that we are now doing real life situation. We are not doing something like length times breadth times height. I want you to see the actual application of the 1D calculation, of the 2D calculation, and the 3D calculation on the very things we all see with our eyes every day, either in the markets, in the stores, in the supermarkets, in our homes. we should be able to do some math about it. Now let's look at the second example. Alexia's bathroom has a tap in the shape of a rectangular prism. And I'm sure most of you have seen these taps before. Okay. With a length of 1.5 meters, a width of 0.5 meters, and a height of 0.4 meters. The moment you see measurement like this, then something should start dropping in your mind. A length of 1.5 meters, a width of 0.5 meter, and a height of 0.4 meter. How many cubic feet of water can it hold? In other words, what is the volume of water that this bath can hold? So we pick our formula, 3D formula. Volume equals the length multiplied by the width multiplied by the height. Then we pick our data. So we have 1.5 meters multiplied by 0.5 meters multiplied by 0.4 meters. Now put them together for me. 1.5 multiplied by 0.5 multiplied by 0.4. Abraham, what are you getting? Or anybody? 1.5 by 0.5 by 0.4. What are you having on your calculator?
So I have 3 over
3,
10.
3 over 10, yes. So 3 over 10 is the same as 0.3.
Okay.
So this is 0.3 meters. Meters are 3 cube.
Yeah.
Very good. 0.3 meters cube. Or the same as cubic feet. 0.3 cubic feet. Or 0.3 meters cube. And that is the volume of water that this can contain. So sometimes you see that the final numbers you get may be smaller than the length or the breadth or the height. It doesn't mean that these ones are bigger than this. No, this one is meters cube. Meters cube is higher than meters. Meters cube is 3 dimension, but meters is 1 dimension. Okay. So 0.3 meters cube means that it's like now when you stand here, the water is going here. The water is flowing here. The water is flowing here. So the water is flowing in a certain diameter, big area, like this. That's the meaning of the meter cube. Okay. It's different from meter, where the water is just flowing on the floor, one direction. This one, it has been trapped in the tap. So that is the meters cube. And so you have it in the bath, somehow like this. Very good. Let's look at another example, real life application. We need to understand some of these things. Now we want to look at a trailer, how to calculate the volume of the other side, the back of a trailer. It says trailers that travel on the road behind tracks are rectangular prisms. A typical height for the inside of these trailers is 2.74 meters. If the trailer is 2.44 meters wide and 6.10 meters long, so look at the dimensions. If the height for the inside of these trailers is 2.74 meters, if the trailer is 2.44 meters wide, that is the width, and 6.10 meters long, what is the volume of the trailer? So you have your 3D formula. Volume equals length times width times height. And then we pick our values. 6.10 meters long means the length. So this is the length. This is the length. 6.10 meters. And then if the trailer is 2.44 meters wide, so that side we are not seeing it, but you see the thing is something like this. This is how the container is looking like. So after getting the length, this would be the width, this side at the back. This would be the width. Okay. This is the length. This is the height. So the width is 2.44 meters. And then the height, which we can see, the height is 2.74 meters. So let's put them there now. I have 6.10 meters multiplied by the width is 2.44 meters. And then the height is 2.74 meters. So I want somebody to multiply these three for me. Let's see the results we have. 6.10 meters multiplied by 2.44 meters multiplied by 2.74 meters. What are you getting on your calculator?
I'm getting 40.78216 meter cube.
Very good. This is a huge volume.
Yeah, I got the same thing.
Yes, so 40.78261 meters cubed. And that's a huge volume. Okay. So in designing the track, they take all these things into consideration. They don't just manufacture anything. They finally ask themselves, what volume at all do we want to hold with this track? And then when they get to know that they need something around 40 meter cube volume, then these are the dimensions they should look out for. You see, you appreciate it when you visit the factories. When you visit the factories, they do something called computer controlled manufacturing. Computer controlled manufacturing. And it is called CCM for short. So what they do is that on the computer, they will do something called simulation. Simulation means that they are trying to make a real life scenario real with computer graphics. So they will tell the system, we want a track, and we want the track to be able to hold liquid of volume 40 meter cube. So they will tell the software that Give us the appropriate length to use. Give us the appropriate weight to use. Give us the appropriate height to use so that we can get our 40 meter cube. And then the software will bring out these numbers. That let's use a length of 6.10 meters. Let's use a width of 2.44 meters. Let's use a height of 2.74 meters. And out of that, they will use it to design the container that will hold the liquid, or that will hold the goods that they put in the trailers that are transported to our various marketplaces. So all these things have an application. If you don't have knowledge about 3D calculation, how do you then instruct the software to give you the appropriate numbers to use? Okay. So in future, you'll be working, some of you will be working with engineers, and you may be seeing some of these things, and I'm sure you will not be a novice when these calculations are being done. You understand what a volume is, you understand what a length is, you understand what a width is, you understand what height means, and you understand how to put all the three of them together to get the final thing you are looking for. Let's close the class with the last example for today. And then I'll open the floor for the last set of questions, and then we can close this morning's class. Now, the last real life example goes this way. It's an aquarium. And I'm sure all of you have seen aquarium one way or the other in your lifetime. And let's see how they are also designed to hold water. An aquarium shaped like a rectangular prism has a length of 120 centimeters, a width of 60 centimeters, and a height of 100 centimeters. How much water is needed to fill the aquarium? How much water is needed to fill the aquarium? So sometimes you may not be around the aquarium, and then they want you to show how much water will be needed. All you need from the manufacturers are the length, the width, and the height of the aquarium. Once you get it, it will be done for you easily. I learned in China, there are some manufacturing companies, if you want to order room furniture, for instance, if you want a sofa for your sitting room, if you want a dining table for your sitting room, if you want a center table for your sitting room, in fact, if you even want what we call the wall design, where you fix your TVs and then your sound system and so on and so forth, all they will ask you is that, give us the length of your room, give us the width of your room, give us the height of your room. These are the only information they need from you. And once you're able to measure the length of your room very well, the width of your room very well, the height of your room very well, they will be able to calculate the volume of your room. And out of the volume, they can send you the appropriate sofa, dining table, and all the TV design you have in your room. Some people use the modern cardboard to do the design. Some also use wood and the rest. Any type you want, they can be able to do it for you. Why? Because you've been able to give them measurements for your room in terms of the 3D, the length of your room, the width of your room, and then the height of your room. So the aquarium design is in such a way that you can at every time know the volume of water you have to fill the aquarium with. And this aquarium has a length of 120 centimeters, a width of 60 centimeters, and a height of 100 centimeters. Let's see the volume we can get out of this. So V is equal to length times width times height. So let's multiply them now. The length is 120 centimeters multiplied by the width is 60 centimeters. And then the height is 100 centimeters. Let's put all these three together. And what are we getting?
720,000.
Very good. 320,000 centimeters cube. 720,000 centimeters cube. Now, I hope I haven't forgotten, but I know that you can check for me. I know that 1,000 centimeters cube is equal to 1 liter. So if 1,000 centimeters cube equals 1 liter, then it means that when we want to change this one to liters, it's the same as 720 liters. And that is a huge aquarium. Huge aquarium, because 720 liters is not a small amount of water. And so if we want to design an aquarium to hold 720 liters of water, all we do is to tell the computer simulation to show us the height, to show us the length, to show us the width before we manufacture the aquarium. Because we need the length, we need the breadth, we need the height to be able to manufacture the aquarium. And that is the last word example I wanted to bring to your attention today. Any question about what we have done so far today, the change of subjects and the dimensions we have done? Yes, Anthony, I see your microphone on. Any question?
Yes, sir. Sir, I wanted to ask this. So far we've done the volume for rectangular shapes or prism. So let's take for instance a figure that is not rectangular. For instance, a taxi, for instance, looking at the shape of a taxi is not rectangular. Can we still work out the volume? For instance,
Yes,
you are giving some.
yes, yes, we can. You are saying a taxi, right?
Yes.
Okay,
Yes.
so a taxi, so this is what is going to happen. Let me try and see whether I can remember my class 1 drawing. So you have a taxi this way. Now remember, in the taxi, there are 3 volumes. So let's say this is the front view of the car. This is where the engine is. Then this is the boot. This is where you put your goods. And this is where the human beings are sitting. So if I say calculate the volume of this car, it is very easy. You have volume 1, you have volume 2, you have volume 3. Okay. So where the human being sits, the middle, you can always know that, assuming I take that one alone out, where the human being sits, it looks something like this when the car is moving. Okay. So you have 3D. You have height, you have length, you have width. Are you with me?
Yes, sir. Yes, sir.
So where you sit, you just picture yourself
So,
when you are
so
sitting.
meaning what you are doing, the shape of a car looks like a box. And what you
Yeah,
are doing.
exactly. Exactly. It looks like a box, but it's a rectangular because you see that where we sit, it's always longer than the seat, like from the back tie, first back tie to the second back tie. I wanted to do some image for you. So let me try. I was trying to do something. Let's say this is the back of the car, and then this is the roof of the car, and then the front of the car. So I was about to say that if the back seat is here and you are seated here like this, isn't it always that the length of the car
Okay.
here, where you sit to the driver, is always longer than the back where the seats are, isn't it?
Yeah, it is. Yes.
Ah, exactly. And so you have the length, you have the width from seat to seat, and then you have the height when you are seated in the car. From the roof of the car to the floor of the car
The
is
floor. Okay. That's the
ah,
height. Okay.
exactly. So that's how they design it. So they will design volume for the back where you put your goods, which we call the boot. They will also design for where you put the engine where nobody can sit. And then they also design for where the driver and the passengers can sit. So you see that the boot has its own length, its own width, its own height. And then where the human being sits also has its own length, its own width, and its own height. And where the engine is also has its own length, its own width, its own height. So at the end of the day, you have three volumes: volume for the boot, volume for the engine, volume for where the passengers and the driver will sit. So it's the same trick. I was thinking you were rather going to ask me to do an example whereby the shape is like a circle, like a football. I was thinking you were going to ask me example like how do you
Yeah.
calculate the volume
Okay.
of a
I,
football
I,
because it is round all over. A football also
initially,
has
I wanted to give a different figure, but I was also thinking probably today you are limiting us to a rectangular prism. That
no,
is
no, no,
why.
no, 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 no. There are all sorts of shapes we could have looked at. So if you take a football falls in the area and volume of a sphere. So when you take a football from end to end like this, we call it the diameter. Now the diameter, you can divide it into two. So one side will be R, the other side will be R. So from the edge of the ball to the center of the ball is R. From the center of the ball to the other edge is also R. Apart from that, the same R can also serve as a height. So from the center to the top of the ball, we can call it H. So look at the direction. You have a direction from the center to the left, a direction from the center to the right, a direction from the center to the top of the ball. So this is also three dimensions. How do you find the volume of this? There's a formula we use. It is 4 over 3 pi r squared h. This is the volume of a sphere, where you are still seeing the three dimension. R squared means that R is in two directions. H means that H is also following its direction. So this is what they use in designing anything that is circular. Example, football. They don't just manufacture football. If they want to manufacture a football of a certain size, they tell the computer to give the R and the H so it can be used to design the football. So if you take a football, you can realize that the football has several transformations. When it is not inflated with air, the size looks like this. When you inflate it with air, it becomes a bit bigger. Now, when you do with what you do with the inflation is that anytime you are inflating a football, you are increasing the radius and the height. And anytime you deflate it, you are reducing the radius and the height. So even if the football becomes flat like this and it's lying down, it still has the three directions. It still has the R to the left, the R to the right, and then the height to the top. So that is how the volume works. You need three measurements. For every volume you do, no matter the shape, you need three measurements. There are others to the way a Milo tin is manufactured. A Milo tin is also manufactured using the three directions. And the formula that is used to manufacture the Milo
So
tin.
sir, please on the volume for the football, the one you gave 4/3 per R square H. How did they arrive at the 4/3? The 4/3.
No, it was derived. This is it. The football, as you see, can be divided into. Let me clean the side, so you can appreciate what we are doing. So if you take the football, can be divided into four. We call them quadrants. So quadrant one, quadrant two, quadrant three, quadrant four. Okay. So for each of the quadrants, if I take it out, for each of the quadrants like this, it looks like a prism. I hope you remember a prism. Do you remember a prism? That thing that we used to draw like this.
Yes, sir.
So each quadrant looks like a prism. And the volume of a prism is 1/3 pi r squared each for one of them. But this time you have four. 1, 2, 3, 4. So you just multiply this one by 4. Once you multiply it by 4, you have what you are seeing here. 4/3 pi r squared each. That is how it was arrived at.
Okay, so the 4 is for the 4 quadrants.
Exactly. Exactly. Okay. So I was about to finish with the Milo tin or any milk in anything, whether Nido or Carvel or whatever, the way they manufacture it. That's what I want to show you. They will never get it wrong. So very simple. Pi r squared each. Very simple. You need the height of the thing. You need a radius. Radius 1, radius 2. Three directions. So first direction, radius, the bottom lid. Second direction, the top lid. and then the height. That's all you need to manufacture the container. And you know the volume of Milo that the container can hold. Okay. So in other words, this thing that we have done, this 3D thing we have done, it is not just for fun. That is what most of the time is used in our manufacturing processes. In manufacturing, there are two things. First of all, you need to manufacture the product. And then secondly, you need to do the packaging. So the packaging is where you have a lot of mathematics coming in, because you are going to package into containers, and all the containers are coming with different shapes, like we are trying to do now. Some of the containers are like a sphere, spherical. Some are also like a rectangle. In fact, most of the containers, most of them are in the form of a rectangle, because it is more easier dealing with rectangular shapes than any other shape, because of the straight formula of length times width. So it makes it more easier to deal with, length times width. And so if one day you become a good manager, one bad thing that our artisans in Ghana are lacking, the artisans we have in Ghana, their major problem is measurement. Sometimes they do not get the measurement right, and then they end up in costing financial loss to you. So you need to train people how to do measurement very well. And if I'm to summarize what we have done, all we are trying to say is that in proper measurement, there are 3 ways of proper measurement. And the 3 ways are as follows. First of all, you need to find the dimensions. You need to know how to do perimeter. You need to know how to do area. You need to know how to do volume. Unfortunately, because of time, I couldn't do examples on area, but area calculations are sometimes, look at the plate you eat in, a flat plate. A flat plate, you can calculate the area, not volume, because it has only 2 directions. It has length, it has width. It doesn't have height. So when it comes to plates, normal plates, flat plates that we eat in, that one you do an area calculation. Now, how do you calculate the area of, let's say, a round flat plate? Very simple. You know the area of a circle, that is pi r squared. So we can use pi r squared to design the plates we have been using at home. So those of you who are women, I'm sure you know sets of plates. Sometimes you have the bigger ones, you have the medium ones, then you have the smaller ones, which we call the saucer. All of them are manufactured using the area dimension, which is pi r squared. So that is also very easy when it comes to area, when we are using area to manufacture a product. Now, what about perimeter? Perimeter is also simple. So an example of a product that has been manufactured using perimeter measurement is our drying lines. The drying lines you buy. Okay. You see that the drying lines you buy, when you are buying them, they are folded. They are folded in a certain way. If you care to know the length, all you do is that you stretch it from one point to the other point. And so probably you were looking for 20 meters. That's very simple to manufacture. Okay, so anything or any product that looks like a line, it means you use the perimeter measurement to manufacture it. Any product that looks like a rectangle that has only two directions, the length and the width, it means you use area calculation to measure it. And then anything that has beyond the two, that has length, that has width, and that has height, it means we need to use the volume calculation to calculate them. And so if I want to manufacture a bed sheet, a bed sheet has only two directions. I just need the length and I need the width, and I'm done with the bed sheet. So that one you use area calculation to do that. So this is very simple. You just have to know which dimension you are using. Are you using perimeter? It means that the product is in the form of a line. Are you using area? It means the product has two directions. It has length and it has width. Are you using volume? It means the product has three directions. It has length, it has width, it has height. This is all you need to know under perimeter, area, and volume. So that is the end of my presentation today. Any more questions because we are done for the day?
So, sir,
Yes, yes.
can we have a figure now to contain all the three?
Yes, that is possible. We can have a figure that can contain all the three. Yes. Yes.
Hello.
Yes.
Yeah. So what he's saying, I was just coming to ask the same, like the car like this. When you look at the car tire, we use the perimeter in calculation for the car tire.
No, the car tire you will not use.
We will not use.
No, you will not use perimeter. Correct yourself. What will you use to calculate the car tire? We pump air inside. Don't you know we pump air inside?
Yes.
Volume, circular form.
So it's volume. If we take a car tire like this.
Yes. Volume.
It's
Yes.
volume. We have air all around. Okay. So I'm happy the way you are brainstorming. This is how I want you to do. That now that we have done this, take every product, take every shape, ask yourself, what dimension is used to manufacture it? Is it perimeter? Is it area? Is it volume? And then you see that a lot of things will come into your mind and you begin to understand how things are done. So the same car, you can have a car light that looks round. Some car light also doesn't look round. It looks rectangular. So all of them, yes, you know that. And then to answer the question he was asking me, let's take a ball. If you take a ball that we fix at our house, the top looks round, the down looks cylindrical. So you have something like this. So somebody will say, how do you calculate the volume of this? You can do it. You divide it into two. You take the circular part. So this side is circular. So you use 4/3 pi r squared h. And then this part looks like a cylinder. So you use the cylinder volume, pi r squared h. So you have volume 1, volume 2. And then you put them together. So no matter the shape, it can be any funny shape. It can be any funny shape. You have maybe probably a box here, you have a circle here, you have a cylinder here, you have a triangle here. You can do all of them are using the same either perimeter, area, or volume. So if you don't even understand what we have done today at all concerning this, just remember that perimeter is one direction, area, two directions, and then volume, three directions. That's all. This is what is controlling every shape. Every shape you want to manufacture is controlled by these three dimensions: perimeter, area, volume. And you get to realize that every time you are calculating perimeter, if it's centimeters, you see only centimeters at the back of the answer because it's one direction. If it's area, it will move to centimeters squared, where the square is telling you that you are dealing with two directions. If it is volume, it will move to centimeter cube, which the three is telling you that you are dealing with three different directions. So by the way you see the unit, you yourself, you know whether this is an area calculation or a volume calculation or a perimeter calculation. And I think with this explanation, we should be fine with these dimensions. All right, so on that note, we will have to end the class today so you can prepare for your next class. I wish you the best of the day, and the class is officially ended. Have a good day.
Thank you, sir.
Thank you, sir.